All right, in section 1.2, we looked at how to calculate the average rate of change. And that finding that average rate of change is important for modeling a lot of different things, including population growth. And those models can look really different. So we could have an exponential model, which could look like the growth goes up, 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 and away. We could have some sort of differential equation, maybe like a logistical model. So our population starts out small, it kind of grows really fast, and then it levels off. You can have a population model that looks like that. You could have a statistical model. There's a number of different ways of representing how population changes. We're going to start with the most basic model, which is a linear model. And the important thing about linear functions is that they have a constant rate of change. Okay, so this is an idea we're going to revisit throughout this class, is that a linear function has a constant rate of change. It's always changing by the same number each time. And the graph of a linear function is a straight line. So if you see something that has a curve in it, that is not linear. It has to be a straight line for it to be linear. So let's look at an example of this. So suppose Gunnison has a population of 8,000 people, and each year the population increases at a constant rate of 200 people per year. So this year we have 8,000 people, next year we'd have 8,200, the following year we'd have 8,400, and so on. So our first step here, we're going to make a table of the town's population every 5 years over a 20-year period, and then we're going to create a graph. So we know our initial population is 8,000. And each year we're going to add 200. So 5 years later, what we're going to end up adding is what 200 times 5 is, which is 1,000. So we're going to add 1,000 people by the time we reach 5 years later. So it would bring us to 9,000. 10 years, we would be at 10,000. Another 5 years goes by and we're at 11,000. And then 20 years later, we're at 12,000 people. All right, and then let's make a graph of this. We'll get our axes going here with our arrows. Okay, so these are the number of years, and we'll put our population on the vertical axis. Okay, so those labels are really important. And then we'll put some marks down here to give us a scale. So we'll call that 20 years because that's the end of our table. And a 10, a 15, and a 5. And we'll do a similar thing on the vertical axis. So our biggest number here is 12,000. So we'll put that at the top of our graph. And that would make this middle mark 6,000. And we have a 3,000 and a 9,000 if we cut each of those in half again. All right, so there is our blank graph. So we're ready to plot our points. So at year 0, we have about 8,000 people. And at year 5, we're about 9,000 people. And I'm going to put one more point out here. Let's see the one for the year for 20 years. That's about 12,000 people. All right, let's see these dots. If I drew my graph decently well enough. Yeah, those dots line up well enough. It's always scary when you freehand a graph. You're like, oh, I hope those dots line up. All right, so there is our graph and table of the town's population. Next question is, what is the average rate of change? So this is a line. So we have a linear function, which means that rate of change is constant. And that's this constant rate of 200 people per year. So the slope of this line is 200, and that's also our average rate of change. So that AVR is 200, and if we put units on it, it would be people per year. Then we need to find a formula to find the population at any given time. So this formula will be P is equal to something. So we know our population starts with 8,000 people. And then we add 200 people for each year. So we would do 200 times the number of years. Right, so there is our formula for that.